Welcome everyone to this new talk of the NAGROM series. Today with us we have Professor Akil Narayan, and he will talk about estimates for Hankel singular value decay of stable dynamical systems. So please, Akil, the floor is yours.
Great, thank you, Maria, and also to the organizers for the invitation to speak in this seminar series. I will warn people, I fortunately didn't set things up so I can't see the chat. So if there are questions, I'm happy for people to speak up at any time. So the first thing to introduce this, I guess I should say these are preliminary results. So you might ask me for a preprint, and we're working on it. We don't quite have it yet, but it's certainly in progress. That also means that this is the first time I'm giving this talk. I'm preparing these slides, so we're all going to find typos together, hopefully not too many. And also you're all guinea pigs for the first time I'm delivering this, so stay tuned. But here's the punchline. The punchline is that really this is about numerical analysis kinds of statements about linear model reduction for linear dynamical systems. So everything here is linear. We're not going to get more complicated than that, basically. But I believe the conclusions of this, the results that we have, are new estimates. So in terms of, say, these first two bullet points, which are a priori error estimates for approximating transfer functions for linear dynamical systems by rational functions of a certain order. This sort of immediately leads us to decay rates for Hankel singular values. So honestly, it's the first bullet point. That's the main punchline. The second one, and also see sort of an extension to balanced truncation. These are immediate corollaries. I should advertise collaborators. So Jan Lai Chen at UMass Dartmouth, Serkan Kugerchin at Virginia Tech, and Fengyan Li at RPI. We've sort of been working on this together. This actually grew out of a semester program at ICERM that happened a few years ago at the start of the pandemic, the COVID-19 pandemic. And this should have been a project that wrapped up at that time, but of course we all got delayed with other things, so it's sort of taking its time. Okay, well, let me go ahead and set things up. So as I said, we're doing everything in the linear dynamical system world. And so I'll try to use this consistent notation throughout, that we have an evolving state, a time evolving state X, that depends linearly, its evolution depends linearly on X, with the addition of a sketch or a linear input with respect to the so-called input function u. So u is an input function that's given to me or assumed known, and this drives the system X. So what we're really interested in is approximating not really the full state, but actually a summary of the state, a linear sketch of it, y, which is an output. Well, yeah, this is the formulation of the problem. This often in the systems community is just referred to as determining the system G as a function, of course, of A, B, and C. The dimensions of these matrices are sort of here on these slides. Probably what's going to be most important for us is capital N. So capital N is the state, the dimension of the system state, which we assume to be very, very large. And typically P and Q, that is the input and output dimensions respectively, these are reasonably small numbers. We're in fact mostly going to assume them to be one, scalar input and scalar output. That's not a technical restriction. It's just one for simplicity. So the main hurdle in this case is the standard one in model reduction, which is that I'm going to assume this is a very large state. So N is, capital N can be thousands, tens of thousands, millions, whatever you like. And we're going to try to talk about constructing ROMs, two-stored models for this particular system. Okay, so here's a very brief and not at all comprehensive discussion of how one might construct a linear ROM for this system. Well, the way you construct a linear ROM is consistent. That is, typically you assume that the full order state X can be approximated by a linear lifting times a reduced order representation x tilde. And then the question is, how do you develop an evolution equation for x tilde? So one way to do it is through what's called a projection-based method, and this compresses the high-dimensional system matrices A, B, and C respectively into sketched versions of themselves, A tilde, B tilde, C tilde. And so basically, I just linearly compress all of these matrices down into a system of size lowercase n, which I assume is much smaller than large n. So and then you can get essentially the same evolution equation. You just put tildes on top of everything. So that's what's at the bottom. And then, of course, the main question is, well, the way that I did this construction relied upon somebody telling me what my compression matrices capital V and capital W are. I didn't tell you what those were. There's, a couple of semesters worth of material in a course to discuss how you construct V and W. And so instead of, I guess, citing every possible person who's done linear model reduction in this way, I decided to only cite a couple of very seminal references for all of this. So, but you shouldn't take 3 references to be an indication of the number of works in this field. It's quite voluminous. So, I'll pause here again to point out that we are really going to stick into the land of linear ROM. So, of course, all of the a large portion of the newer research is going into nonlinear ROMs, essentially circumventing linear model reduction restrictions, so-called McGraw-Fenwick barriers, things like this. We're not going to go there at all. We're going to stick to the land of linear ROMs. And again, the goal is actually to present some new analysis. So I'm going to talk about one particular way in which these matrices, capital V and capital W, are constructed. And this is done through a control theoretic point of view. You look at the Gramian matrices of the system, so the reachability and observability Gramian P and Q respectively. So you could take these integral formulations as definitions, although there are slightly alternative ones sometimes that you see in the literature. I'm going to assume that the system is minimal, so these matrices P and Q are invertible. They're square matrices whose size is the original system, so they're large capital N by capital N matrices. I'm going to assume they're invertible. And these matrices tell you something about energy, essentially. And so to summarize things, essentially, the so-called reachability, Gramian capital P, tells you something about the energy required in terms of an input U in order to reach a particular state Z when you start the dynamical system from the origin. In sort of a different framework or a different point of view, the observability Gramian Q tells you about the energy, the norm of an output, that's Y, when you start from a particular point Z without forcing. So these two large N by N Gramians tell you something about energy either you have to put into the system or take out of the system in order to achieve certain things, essentially reaching certain states. What's particularly important, let's say from the computational point of view, is that although there are these integral formulations of these matrices, what's more useful from the computational point of view is that you can compute them as solutions to the Lyapunov equation. So this is typically what's done as long as the system is not too large. Okay, so you can analyze these matrices and compute them is essentially the point. So probably the poster child for Gramian-based analysis of model reduction is called balanced truncation. And so this is the punchline. It's a particular construction of these compression matrices V and W that I introduced before. And so the basic idea is that remember that P and Q tell you something about input and output energy. And so it turns out if you study a generalized eigenvalue problem that corresponds with balancing Q and P, then you can use this generalized eigenvalue problem to transform the original system into a new system of the same size. But in this case, the reachability and observability Gramians are identical and diagonal. And so the reason that's important is that you can sort of say, well, it's easy. There's no question about balancing things anymore because things are balanced. I have an exact understanding of input and output energy flow based on certain states in the system. And so then balanced truncation first balances. That's essentially this formulation, roughly speaking. And then you truncate. So you simply remove a bunch of degrees of freedom because everything's balanced. And that gives you a reduced order model of size lowercase n. There's a lot of linear algebra that goes in the back end of this that I'm not going to provide with you, but the main point is that somehow you can use the solution of this eigenvalue problem to construct V and W. And so that's, sort of the main punchline. So the eigenvalues, or rather their square roots, in decreasing value, these play a particularly important theoretical role. These are called the Hankel singular values of the dynamical system. The reason they're called that is that they are singular values of an infinite dimensional Hankel operator associated with the system. So they are singular values in a very real sense. And one of the sort of very amazing things about balance truncation is that you come out with an error estimate, which basically tells you that if I were to form an order n reduced order model, that's y sub n, and I compare that with the output of the original full order system, then the mistake I make in that output scales, linearly with respect to the input. That makes sense. But the price that I pay is essentially the sum of the trailing singular values, Hankel singular values. So this is sort of very much what you would expect from standard low rank matrix approximation. The theory behind this is a lot richer in order to reach this point. Essentially, you get something that looks very familiar. And so this is kind of the big exciting thing about balance truncation, is that you can sort of explicitly compute these V and W matrices, and you can explicitly come up with an error estimate because these Hankel singular values are eigenvalues. So of course you can compute them. In this talk, we're going to take a complementary viewpoint, which is to say that, well, if I want to get an error estimate involving the error of the output relative to the input u, I can do something different. And that's simply by writing things in the frequency domain. So I'm going to take the Laplace transform of everything. I'm going to define the standard transfer function h. And so this is just the linear algebraic version of what happens when you take derivatives in the Laplace transform domain. And this immediately tells you through submultiplicity of matrix norms that if I can get a handle on approximating the transfer function, then this gives me this epsilon bound, the same multiplicativity bound on approximating the output y. Okay, and so you have to introduce some norms here. So there's so-called the H infinity norm of the transfer function, which is the maximum norm of the transfer function along the imaginary axis of the complex domain. So we're going to take this complementary viewpoint for most of the rest of this talk. That is, I'm going to try to understand how to do H infinity approximation of transfer functions. But of course, this will then immediately give me something like this, right? Some kind of error decay bound like this. Okay. And maybe in the interest of pointing out what is important in terms of all the technical details on this slide, maybe it's worth internalizing the H infinity norm definition, because I'll be referring to this quite a lot. So it's important to remember what it means. Because of this decay bound for balanced truncation, then you get the idea, which is in fact true, that if the Hankel singular values decay quickly, then balanced truncation and indeed many other projection-based model order reduction methods are in fact effective. And so, well, on real examples, you get certain kinds of behavior. So on the right here, I've shown you 3 examples. There are 3 plots colored red, blue, and black. And so the blue curve has very quickly exponentially decaying Hankel singular values. The red curve has sort of exponentially decaying Hankel singular values. And the third one has singular values which sort of decay, but very, very slowly. You need something like, if I eyeball norm it, maybe 100 degrees of freedom to gain an order of magnitude in terms of the singular value decay. And so this is not that good if you look at the black curve, for example. And so any of these situations happens with real problems. And so you might ask, well, okay, how can I get an intuition for when this happens? That is, when is the Hankel operator low rank, basically. And if you talk to people, you'll certainly hear a lot of what I would call qualitative expressions of when this happens. So for example, a pretty common one is to say that, well, you'll get slow decay of eigenvalues when a lot of the spectrum of the state matrix A is close to the imaginary axis, and say they're all spread out vertically. So if they're all very close to the imaginary axis, but cover a wide vertical range of the imaginary axis, you would expect slow decay of Hankel singular values. You can sort of twist this around and say, well, essentially what this probably means is that if the eigenvalues, the spectrum of A, are, say, on the real axis going off towards negative infinity, then this is sort of diffusive behavior, and you would expect low rank methods to work well, low model reduction methods to work well. But if you have spread along the imaginary axis, this is transport-like behavior. And in this case, you don't really get efficient model order reduction. And this jives, I think, with our common understanding of when, say, the Kolmogorov width decays quickly and when it doesn't. So this is not terribly surprising, I think. But this sort of begs the question, can we say something more precise about when Hankel singular values decay quickly and when they don't? Well, there's a reasonable amount of work on answering this question. When do we know that Hankel singular values decay quickly? I think one of the first results that I'm aware of, anyway, I'm happy to be corrected, is by Theo Penzel, who bounded this decay based on sort of explicit formulas in terms of the condition numbers of a symmetric matrix A. So if you have a symmetric A, you can sort of compute bounds for the singular values based on that condition number. There's some work a little bit later that sort of dealt with actual explicit decay of Hankel singular values, and they can sort of show that there's a statement that Hankel singular values decay super polynomially, so that they decay faster than any polynomial function, or that they decay root exponentially, so like e to the minus square root of n, something like that. And so these are sort of explicit formulas, but they're not explicit in terms of the rate. So you can sort of get the rate out if you read these papers, but to me, it's not very transparent. And then maybe there's this last one, which is about system invariance involving majorization properties. This one leads to essentially explicit bounds, but I believe it's sort of opaque in terms of how you get decay rates in this. So, if I were doing real justice to the literature, I would spend a little bit of time and talk to you about all of these things individually, what all these estimates give you. I'm sort of going to sweep these details under the rug for now, and we're just going to power on forward. But I do want to tip my hat and say there are some estimates already out there. And in particular, the main point of this talk is we're actually going to prove something like this decaying exponentially thing, but we're going to get rid of the root. So we actually have strict exponential decay. So, all right. So this is the main question we're going to ask, which is, how quickly do Hankel singular values decay? And the way we're going to do this is going to seem a bit strange. So I'm not going to try to investigate Hankel singular values directly. That's not what I'm going to do. Instead, I'm actually going to try to do H infinity error estimation of the transfer function. And that is going to turn out to lead to estimates of Hankel singular values. And this actually is a general statement that we're going to derive, or we're going to present on rational approximability of transfer functions by rational functions. So to me, I think it's a maybe not entirely new result, but at least a new statement, let's say. So this is now we finally come to what maybe should have been the introduction slide, which is the following. So what am I going to talk about for the remainder of the time that I have? And that is, I'm going to specialize essentially to single input, single output systems. So this is where the dimension of the input and the output are 1, P and Q is equal to 1. And I'm going to present at least what I'll call a priori H infinity approximation error estimates with rational functions. So essentially, I'm going to talk about how we construct reduced order models, linear reduced order models that approximate the original system in terms of the transfer function. This is sort of, as an immediate corollary, going to lead both to error estimates on estimates on the decay rate of Hankel singular values. It's also going to lead immediately to balanced truncation error estimates because we sort of showed those before. I'm going to talk a little bit about how we generalize. So this dissipativity assumption is pretty strong. This means that the numerical range of the system matrix A is in the left half plane. But we can relax this to just stable systems. That's not too difficult to do. And you get essentially all the same statements that you did with the dissipative case. I'll tell you a little bit about the proof. I'm not really going to go through details because that would be way too much. But I'll tell you a little bit how this comes about, and what's sort of to me at least unexpected is that you actually do have to care about Kolmogorov n widths in this construction. So this is sort of this way that I presented all these mathematics is not really in the parametric snapshot based reduced order modeling community. So I'm not really using the notion of Kolmogorov n widths or solution manifolds or anything like that. I'm using control theory, systems-based methods, but you can sort of bring these ideas together, it turns out. And then I'll just sort of briefly say that, hey, look, we can actually do this for very, very general systems. But I won't really present details for that. Okay, so what's the essential idea? Here's the essential idea. So I'm going to essentially talk about system matrices A that are sectorial. So what does this mean? I'm going to start with a system matrix A. So again, this is the x prime equals AX matrix. So this matrix A, I'm generally going to assume that the eigenvalues lie in the left half plane, so that energy doesn't increase on the system. But more than that, I'm going to start by assuming not just that the spectrum lies in the left half plane, but that the numerical range also lies in the left half plane. So this is just an initial assumption. So W of A here is my notation for the numerical range. This is the image of the Rayleigh quotient. And so this is a compact convex set of values in the complex plane. That's this big red ballish looking thing on the right. I'm going to assume to begin with that this numerical range lies to the left of the imaginary axis. So in this picture, I didn't draw it, but the imaginary axis would be something like here on the, intersecting with this I omega point. And so it turns out that, okay, if I assume that the numerical range lies entirely in the left half plane, then the operator A is sectorial, which means that its field of values can be enclosed in a conic sector in the left half plane whose vertex lies on the imaginary axis somewhere. Okay, so what this statement sectorial is saying is that there's a conic region, which is this blue shaded region here, that entirely encloses the numerical range. And there are two parameters defining this conic region. One is its vertex, the location on the imaginary axis omega. And the second thing that describes it is essentially the angle of the opening of this cone. The way I'm going to sort of write that down is I'm going to say, well, A is an element of S lowercase w of M. So this is meant to be, it's a sectorial operator with respect to its numerical range with the angle parameter M. Okay. So M, you'll notice, is not actually the angle, it's the arctangent of the angle. And that's just to make analysis less technical. You can sort of peel this apart a little bit and convince yourself that the sectorial condition is equivalent to the matrix being dissipative. So I'm just assuming that the numerical range is in the left half plane. That's fine. As I told you, there are two parameters that describe the sector, omega and M. We're going to ignore omega. Omega doesn't really tell us a whole lot. It essentially tells you the translation location of the numerical range, which is not too important. But the angle is very important. So M, this number M, is in fact, it's going to form the core of what we do. One thing to point out here is that, of course, the eigenvalues, the spectrum of A, lie within the numerical range. So it's certainly possible that a matrix can be stable, that its eigenvalues can be in the left half plane, but the numerical range bleeds out into the right half plane. So we aren't really covering all dynamical systems with this definition that we're interested in, but we'll get there. Just for now, we'll do with this. Okay, so here's where I think all of the essential intuition is through these last 2 points on this slide, which is that when M is large, so M being large corresponds to large angle here. And so if the angle is large, that means that the cone that I need is very large vertically speaking. And so the numerical range has large vertical spread, so to speak. A small value of M, on the other hand, tells me that essentially I can take a very thin cone and confine the entire numerical range into that thin cone. And so this is very much like a diffusion operator. And so what you should expect intuitively is that when you have large M, model order reduction is hard, linear model order reduction is hard. And when you have small m, linear model order reduction is, quote, easy. And that is, in fact, the punchline. So that's exactly what I'm going to show you with more technical language. Okay. One final thing before we get on, I'm going to present the main statement next, but before we do that, let's introduce some notation. So based on this definition of a sectorial operator, there are some summary parameters that tell me something about the sectorial nature of this problem. One is so the numerical abscissa, which is essentially the real value of the rightmost point in the numerical range. So red was a bad pointer color to choose, but you can tell here that I'm just doing things on the very right-hand side. I need the numerical radius, which is simply the maximum modulus of all the entries in the numerical range. And then I need something a little bit weird. I need something that is the numerical radius scale divided by the numerical abscissa. So I've called this kappa because it kind of sort of is a condition number. That's, I'm not going to call it a condition number after the slide because that's wrong, but you can think of it sort of like a condition number, I think. So I'm going to use these three quantities: eta, which is the numerical abscissa, rho, which is the radius, and kappa, which is some ratio of these two things. Okay, so here's the main estimate. It's the following. So let's assume that A is in fact a sectorial matrix, sectorial operator. I'm going to specialize the CISO systems, again, mostly just for, for ease of technical statements. And recall that by me assuming that A is sectorial, I am assuming that the system is dissipative. So its numerical range is in the left half plane. Okay. Under those assumptions, then there exists an order n transfer function that corresponds to a stable dynamical system. So that's what this sort of notation under the infimum means. There's an order n transfer function that is a stable dynamical system, such that if I replace my original system's transfer function h with this approximation, and I look at the error in the h infinity norm, this should be a subscript, sorry about that, h subscript infinity, then this error scales like the right-hand side. Okay, what's in the right-hand side? All right, there's a bunch of constants. That's fine, involving the input and output matrices C and B. There's a universal constant C1, and then there's this ratio. So this ratio is itself this quote condition number kappa, normalized by the abscissa. So this is just a constant. I'll just leave it for now. I'll just leave it here. What's really important is what's inside this exponential. So there's a log term. I'm going to ignore the log term, but if you ignore the log term, this says that this approximability can be attained exponentially in terms of the order n, and it's discounted by what I'm calling m tilde, which is essentially the slope of, which is exactly the slope of the sector. So in other words, large m, in this case, corresponds to slower decay of this error bound, and small m corresponds to faster decay of this error bound. Okay, and this is the quantitative version of what I try to convince you of qualitatively on the previous slide. So I'm taking m tilde here to be a truncation of m. I can't take m all the way down to 0 in the analysis because things break. So you need to truncate it. I truncated it to value 1. Okay. These constants C1 and C2 are not scary looking. I forget the numbers. C1 is maybe something like 12 or 15, and C2 is a bit not nice. It's something like 1/50 or something like this. But it's not, if you look at the literature on things like compressed sensing, you'll see absolute constants floating around everywhere, and these absolute constants can be on the order of 1 million. That's not the case here. These constants are, let's say, order 10, something like that. Okay. So I'm going to leave this up here for a while because there's a lot to talk about. So the main point here, again, is that this tells me exactly about how I approximate transfer functions by stable transfer functions. So I'm assuming that the full order model is dissipative, so I'm being a bit restrictive here. But under that restriction, then I'm able to approximate things with stable transfer functions of smaller order. And the way we do this, so I'm going to give you sort of a high-level description of the proof. High-level description involves actually constructing an explicit reduced order model that achieves this error bound. So that's basically it. Finally, this truncation value. So I have this truncation value of 1 here. The number 1 is not important. It's just a convenient number to choose. You can make it smaller or larger. It'll just affect the constants in the analysis. That's all. Okay. Some things to point out explicitly here is that there's nothing here on the right-hand side that explicitly depends on the full order parameter n, capital N. So this system H here is of order capital N, but there's nothing here that depends on capital N. Okay, so that's sort of what you would expect. That's good. The rate of decay, so this m tilde thing, and even the log terms here, if you take the log terms back into your consideration, this thing in the denominator, this rate depends only on A. It actually doesn't depend on the input and output matrices B and C. This is a little bit suspicious, but I'll show you later that there is not in this particular estimate, but in say the multiple input, multiple output MIMO case, you'll sort of see dependence on B and C bleeding back in. So the main point again is this third bullet point, which is that if you sort of ignore all the things that don't matter, this is essentially exponential decay, like lowercase n divided by lowercase m. So that's basically the point of this particular statement, which yields, again, sort of an explicit decay rate. It's the sectorial parameter m. And okay, last sort of quizzical thing is that I just care about the numerical range here for this particular statement, but the spectrum of A I don't care about. I don't care where the eigenvalues of A are located. That's not relevant for this statement. Okay. All right, so here's where we use this immediately to talk about singular values, Hankel singular values. So I'm going to leverage a very classic theorem, the Adamian-Aref-Krein theorem, the AAK theorem, which tells me that, well, if I actually try to compute the H infinity minimal error over order and transfer functions, this is exactly equal to a Hankel singular value. So on the previous slide, I exactly had an error estimate for this minimum over here. And so in that case, I'm simply going to replace that minimum with the singular value. And so you get essentially the same error estimate for the Hankel singular values. And so note, I've simply replaced the left-hand side by the Hankel singular values. So that's it. That's an easy way to get to transfer from H infinity error estimation to Hankel singular value estimation. So if you're familiar with Hankel singular values, you'll realize they have some invariant properties. That is, if I scale, if I multiply the system matrices by certain constants, these scaling constants come out in terms of the Hankel singular values. And so this is this statement right here. That is, if I replace A with 1 over K times A, or B with K times B, or C with K times C, any of these replacements get me a multiplicative factor of K out at the end. And this bound, if you sort of go through all the, essentially it's these constants out here, all of these constants obey exactly the scaling property as well. So everything works out, so to speak. The bound is has the right units, if you want to think about it that way. Okay, a final sort of corollary is an application to balanced truncation. So remember before that I advertised that balanced truncation has an explicit error bound in terms of the trailing sum of Hankel singular values. Well, you simply use that error estimate that we have directly into that statement, and that immediately tells you that if you exercise balanced truncation, then the error that you commit has an explicit bound. Okay, so that's sort of nice. So this doesn't involve singular values, which I don't know, which I haven't computed yet. I sort of have to do some computational analysis to compute them. I get an understanding of this decay rate immediately without doing any of that. So that's kind of nice. And now I've gotten a bit sloppy and I've hidden all the constants from you that I think don't matter. And that, of course, is because in terms of this estimate, they don't really matter. Okay. So that essentially, I've started with a dissipative system. So A has its numerical range in the left half plane, but that is essentially a tour of the main results. I've put a bunch of assumptions along the way. I've made it CISO. I've made it dissipative. I'm slowly going to start pulling those out now, pulling out those assumptions. So what can I say about, say, non-dissipative systems? Well, you make a similar definition as we saw before. So instead of the matrix A being sectorial, that is, its field of values lies in the left half plane, I'm going to assume, so I had to make up a term for this. I was unable to find a particular term that mirrored what I wanted here in the literature, and I'm happy if somebody is able to come up with one or tell me that something exists. But we're going to call a matrix spectrally sectorial if this sectorial property, this inclusion inside a sector, holds not for its field of values, but for its. So this whole slide is exactly the same slide as we saw before, except that I've replaced instances of capital W by lambda, which I term to be the spectrum of A. And so everything else is the same, except that, well, if I were to really draw this, all I care about is the spectrum. So these little black X's all over the place, that's the spectrum of A. And so really I just want the cone to enclose these. With a little bit of convex geometry, you can convince yourself that that's the same thing as enclosing the convex hull of the spectrum with this cone. And so that's what I've drawn in the figure. That the spectrally sectorial condition is equivalent to tightly enclosing the convex hull of the spectrum inside a cone. Again, you can sort of peel back all the layers here and convince yourself that if a system is asymptotically stable, which means that the system matrix A has spectrum entirely in the left half plane, in the open left half plane. So if that system is asymptotically stable, then it's the same as saying that A is spectrally sectorial. Of course, the value of M is what plays a role here. And again, the value of omega in this particular construction doesn't really matter at all. Okay. So same kinds of derived quantities as before. We've got the spectral abscissa, that is the maximum real part of the eigenvalues. We've got the spectral radius, which is the maximum magnitude of the spectrum. And then I've got something that's a little bit different. Well, it's not a little bit different, but it means something a little bit different. This is a measure of the spectrum of A, the size of the spectrum, and it's simply the radius divided by the abscissa. And again, I'm simply making this definition for convenience, and looks like we found another typo. This should be K sub lambda, not K sub W. So sorry about that. So I'm just doing the same things, and what I'm going to show you on the next slide is the same error estimate, but basically everything is replaced by lambdas instead of W's. Okay, so that's that. So again, I'm now assuming that A is spectrally sectorial, so that's the S sub lambda, not the S sub W. I am making sure that the system is single input, single output. And I'm making an additional assumption here that A is diagonalizable. I don't need this assumption, but again, I just don't want to state the more general formula. The more general formula is more painful. So I'm trying to simplify things. So if A is diagonalizable, then again, it's the statement about H infinity approximation of the transfer function. And this is in terms of, a bunch of constants out front, and then you get the same rate, e to the minus n divided by m. Okay. I'm still doing all the same tricks. I'm truncating. There's one extra addition here, which is that I've introduced what I've seen called as the Jordan condition number, sometimes the eigenvalue condition number. This is the standard smallest condition number of a matrix that achieves a diagonalization of A. And so that appears, here somewhere. So anyway, that's fine. The main thrust of this result is that, in fact, I've generalized things from the distributive case to the spectral case. So that's really good. And if you sort of think about the fact that the spectrum of A is included within the numerical range, you'll slowly convince yourself that m sub lambda, so the spectrally sectorial m parameter, is smaller than the standard sectorial m parameter. And so this is, technically speaking, in terms of decay rate, this is a sharper estimate because you can get a smaller value of m. Okay. I won't present them to you, but of course, you sort of immediately get the same things that we got before: Hankel singular value decay rates and sort of explicit error bounds for balanced truncation. And it's the same machinery as before. So I won't really harp on it too much. The one thing that, well, there are a couple of things to sort of realize. One is that when I did the spectral approach, I sort of injected this Jordan condition number of A. This, so again, this is the condition number of a matrix which diagonalizes the system. And it turns out you can make this condition number arbitrarily bad, even if A has finite dimension and is pretty well behaved. And so you can sort of explicitly construct an example like this, where this Jordan condition number is as large as you want. And you know, that's not good. So we do have, unfortunately, this multiplicative dependence that's additional here. However, I should point out that I I'm really not trying to convince you that any of these estimates are generally sharp. So in other words, I'm not trying to convince you that if you have knowledge of this parameter m, this immediately gives you, say, useful quantitative information. I don't expect that to be the case, and that's because these results come through a whole chain of estimates, and some of these estimates are sharp and some are not. And so we've accumulated a bunch of non-sharpness in the way that we derive this. So there's no reason to believe that this is a sharp estimate at all. However, it is a generic estimate that holds for a very broad class of systems and is informative in terms of the sectorial parameter m. Okay. So, you know, how useful are these? Are these useful at all? And for the quantitative point of view, maybe, I don't really know. Here are some values of M that I've compiled from some of the standard benchmark problems in the Slycott database. Remember that S sub W denotes the standard sectorial condition, which is containing the numerical range, and S sub lambda denotes the spectrally sectorial condition, which means containing the spectrum. And so, of course, it's true that the left column M sub lambda is definitely smaller than or equal to the right column M sub W. And in fact, for many of these examples, they're not dissipative. And so the parameter m is actually infinity if you want. It's not infinity technically; it doesn't exist. But anyway, I can't report it. However, if I simply say look at the spectrally sectorial parameter, you'll see that okay, for some nice problems like the continuous heat equation, m is 0, which is fantastic. For some PD examples, it's maybe 10 to the minus 1. Okay, that's good. There's some models, say the ED in the building model, it's 10 to the 1. Okay, that's acceptable. And then there are some like a modified nodal analysis problem where it's 10 to the 10. Okay, and obviously 10 to the 10 is not a terribly useful estimate because remember, the error estimate tells me that it's e to the minus n divided by this number m. So if this number m is 10 to the 10, this is a very bad error estimate. So that's essentially what this point says here, which is that if m is large, this is not a useful bound at all. Okay, but it's certainly true that for some models we have sort of a reasonable value of m here. I should mention I didn't sort of explain this, but you can compute. So of course, computing m for a finite spectrum is not that big of a deal. It turns out computing m for a compact set, a general compact set, the numerical range, that's also not too difficult. So you can come up with algorithms to do this. It's not that bad, I would say. Okay, but there are sort of easy examples that actually show you that this can't possibly be sharp. So the Pencil model is a dynamical system model that has an evolution matrix A that is normal. So the numerical range and the spectrum coincide. But it has spectrum that lies along the negative real line, so that's good. And then it has two eigenvalues that have very large imaginary parts. So those two eigenvalues that have very large and small imaginary parts make the m parameter in this analysis very, very large. Whatever you want, 10 to the 10 or something like this. But from practice, you know that doing something like balanced truncation on the Pencil model is reasonably effective. It's not that effective, but it's reasonably effective. I didn't make slides to show you this, but our analysis actually handles this case as well. But you have to be more general about how you present things. So the way that I presented things uses simply this summary parameter m, and this summary parameter m is not enough to handle something like the Pencil model. But you can actually circumvent that. But it takes a lot more technical setup, so I didn't present it. So anyway, but if you just take the main point of this bound in your mind, then well, that's a problem, so to speak. That the Pencil model won't do it for you. Okay. So I only have 5 minutes, and that's okay. I won't. I'm not really going to go into the proof, but I do want to make a few remarks about things in the proof. The first thing is that all of this really boils down to the first statement I told you, which is the bound on dissipative systems. So the bound on stable systems is sort of a direct corollary from that. When I say direct corollary, there's a lot of work that has to be done, but there aren't any new ideas. So really, the main goal is to do this for a dissipative system. Once you can do it for a dissipative system, it works for stable systems with a lot of setup. Okay, and here's essentially it's a three-step process for the proof, and here's basically the whole idea. Uh, so there are three things to do. First is that, well, you view the transfer function as a map from a set, the real line, on into the set of complex numbers. And in particular, you can view omega as a parameter. And so then the goal is to do a parametric approximation. So this is essentially viewing the problem as a frequency domain parametric problem. This is not a new idea. There are lots of people who have thought about looking at systems-based model reduction from the frequency domain, viewing the frequency as a parameter. This is not new at all. And in particular, Ricardo, I think 2 weeks ago in this seminar series, told us about one way in which he's looking at that. And so, yeah, this is not a new point of view, certainly. The second thing, once you set it up as a frequency domain parametric problem, is that you use what would be sort of a standard reduced basis method construction in order to construct an order n ROM. So you just use a greedy approach, nothing more to it. And of course, this is not new at all. This is something that people have been looking at for the better part of 3 decades, maybe. So this again is not, I think, too terrible of an idea. The third thing is that it turns out once you do the first 2 steps, you get an error bound that's in terms of the Kolmogorov n-width of a certain parametric manifold. So the third step is to estimate that parametric manifold. You try to compute the n-width decay of that. And again, this is not a new idea. There are lots of people who have computed or analyzed decay rates of Kolmogorov n-widths, and you can come up with bounds on this. And in fact, most of the technical ideas that we have stem from the work in these particular papers. So the real point of me putting all these references on the slide is to try to convince you that it's possible, I'm not actually sure, but it's possible that what we've presented is a new error bound on things, but the ingredients, all of the essential ingredients are very old ideas. We're not coming up with anything particularly new. We're simply we're coming up with a new way of combining them together. Okay, so I think I did sketch out some things in the proof, but I'm going to skip over them. This picture is sort of interesting. It's kind of the main idea, but we're just going to skip over it. Sorry about that. One final comment is that we don't need single input, single output. In fact, if you do things at the multiple input, multiple output case, basically what happens is that, remember that P and Q are the dimensions of the input and output. You take the minimum of those numbers, and that number essentially gets shoved into the denominator of the decay rate. It also gets, put out as a multiplicative constant, but this is not that important. What's really important is the 1 over P tilde in the decay rate. And that's it. So really, it's perfectly okay that that the matrix is multiple input, multiple output, and A doesn't have to be diagonalizable. There's a way to handle the non-diagonalizable case, which again is not particularly pleasant to present, but you can do it essentially. So here is what I think is a reasonable summary of what I've talked to you about today, which is that I've tried to communicate to you what I think is a fairly different, let's say, method of talking about order n or order n h infinity rational approximation of transfer functions. I am restricted to finite dimensional systems, so I actually do need the system to be finite dimensional, the full order system, and not infinite dimensional. And there's a technical reason for this. I think we can extend it, but I'm not sure. So this rational approximation statement immediately tells us something about decay of Hankel singular values, which is good. It also immediately tells us something about error of balanced truncation. And again, this is not, I don't mean error error estimates for balanced truncation in terms of singular values. That already exists. We have error estimates for balanced truncation that don't use singular values in the explicit estimate. So it's kind of interesting. But from a practical point of view, I'm not convinced that these decay rates are really interesting for practical benefit. That is, I can't imagine a pipeline where somebody's going to try to construct a reduced order model by first computing M factorial parameter and then determining if it's useful or not. Like, I don't think that's a good way to go. So I'm not really sure that this is of practical use, but it is, I think, actually of theoretical use. Just sort of interesting to know when model order reduction in principle is possible. By the way, the construction that I came up, I didn't present to you in the proof here, is exactly a simple Galerkin reduced basis method ROM. So there's really nothing complicated about how it actually works. I'm pretty sure we can extend this. So instead of doing H infinity approximation, I think we can do H2 approximation. This is something to require some work, but I think it can be done. Of course, this immediately suggests that we can do parametric systems. So nothing here was a parameter in what I've done. But of course, we can put parameters in the dynamical system. I think our analysis can handle this quite simply. Infinite dimensional systems, I'm not sure about. That one requires a little bit of thought. But of course, the next question is, well, can you turn these kinds of things into algorithms that are certifiable? Right? That's kind of one of the main selling points of reduced basis methods, is they're certifiable. We'd like to be able to do that for this particular algorithm. Okay, well, thanks for your time. And yeah, I'm happy to take questions if there are any.
Thank you, Akil, for your talk. So now, as you said, it's question time. So if you have questions, please unmute yourself and you can ask directly to the speaker. Mattia?
Yeah, I have a question. Thanks for the presentation. It was very nice and very clear. I really like it. So what I want, as far as I understand, so the bound you showed, so basically you have exponential decay there. Of course, then it depends. There is just some depends on the problem appearing in this K of W and the others. So like what I wanted to understand is like if you have something coming from a transport problem, so these bounds there hold, so you also, I mean, they also tells you that you have this exponential decay there, which probably will be slow because of the factor will be large, or these
That's correct.
Applied there. How it is?
Yeah. Thanks, Mattia, for the question. Yeah, what you summarized is correct. So this, strictly speaking, tells you that there's always exponential decay, but this number can be so large that it's essentially not observable. So in one of the examples I gave here, this is just numerically speaking, so I wouldn't really say that this black curve has exponentially decaying singular values, but if I make the decay rate slow enough, then I guess you could call it exponential decay. Right? That's kind of the point.
Yeah, this is interesting because, like, for instance, from the reduced basis community, like you have polynomial decay there for the transport, right? And exponential decay for diffusion. But here I see that it's more, I mean, it's clearly not the parameter, it's time. So, yeah.
Yeah, and another technical thing, so that's a little bit different, say, from the reduced basis community, is that so here in this particular case, I'm restricting myself to finite dimensional systems. So there are only a finite number of Hankel singular values. In in a continuous reduced basis problem formulation, the parametric manifold is infinite dimensional. So I can't actually generally reach zero error. I have sort of things, if you want, singular values that trail off towards infinity. And that's why you can make very formal statements about things like polynomial or exponential decay. In this case, I have a finite number of data points, Hankel singular values. I can say that they decay exponentially or algebraically or basically whatever I want, as long as I tune the decay rate constants well enough. And this statement is about essentially tuning the decay rate constants, tuning this decay rate constant in a way that says, okay, well, strictly speaking, they decay exponentially. But that parameter is so large that the exponential decay doesn't look exponential at all.
Yeah, I see. Thanks. And actually, I have also another question, if possible.
Please, go ahead.
Yeah, it's more a curiosity. Like, can you just sketch, saying briefly, which are the main ingredients for the proof of this?
Sure. I'll just reveal the slides that I skipped over. So
exactly.
let's
I was
see here.
interested.
Yeah. So okay. The first step is just the parametric viewpoint. So essentially, the transfer function is the C matrix times very large dimensional vector. That's this W. So and then the point is that this guy is the solution to a parametric linear problem. And so then you just play reduced basis. Essentially, you say, well, I'm going to greedily select parameter values, form subspaces, and then compress the high dimensional W formulation to a lower dimensional formulation. That's step one. Step two is to say that, well, you actually have to do some work. This is not quite straightforward, but you sort of have to show that the difference between an n-dimensional approximation that we just constructed and the original solution decays like the Kolmogorov n-width. So this uses results of like Peter Binev and Ron DeVore and Albert Cohen that have explicit estimates on greedy algorithms and how they behave with respect to Kolmogorov n-widths. So that's step two, writing things in terms of the n-width. And step three is just estimating the n-width. And that's this fun picture here, which is essentially that I'm trying to estimate the n-width where the parameter is in an unbounded parameter. And so I can't use sort of standard tricks where I just, take a disk and make sure that the region that I care about is enclosed in the disk and then do polynomial approximation on that disk. Because the disk needs to have infinite radius to encompass the whole imaginary axis. So instead, the trick is that we used anyway is to use several disks and just enclose the entire imaginary axis. And these angled lines here are meant to represent the sector boundaries, and that's where the sectorial condition comes into play. I essentially need the distance from these disks to the sector to behave in certain ways, and that sectorial parameter is what allows me to construct the disks in the right way. And if you put all that together, then you get an n-width decay that looks like e to the minus L, where L is equal to n divided by the number of disks k that you used. And then you can show that k looks like m. And so then you get e to the minus n divided by m, basically.
I see. Yeah.
Yeah.
Thank you.
But thanks for the questions. Yeah.
Are there other questions for Akil? It seems that it is not. Oh, Narayan, please go.
So I can ask a follow-up question maybe. So very nice talk, Akil. First of all, I mean, this was an excellent talk. Thank you. Really nice.
Thank you.
So the question I have is related to Matthias' question, I guess. So you do make an effort to kind of like discuss both dissipative systems and those that involve transport and convection. And so, but my question is, I didn't quite understand, maybe I missed it. Do you actually separate the two? So, or do you consider them together and then just look at the character of the operator, the matrix, and in different scenarios? Or do you actually separate them? That's my question.
There's no separation, no. So the separation, if you want, is an imprecise quantitative separation, and that is done by for example, in the spectral case, I simply say that look, if the eigenvalues are vertically spread out along the imaginary axis, I say that this sectorial parameter m is large. And if they're not vertically spread out along the imaginary axis and instead say just along the negative real axis, that would be diffusive case, but I just say that that's a small value of m. So that's the quantitative way in which we separate the diffusive versus convective behavior simply by describing it as this parameter m. It's an imperfect description because, again, I sort of said, well, there's a particular model, the Penziel model, that's dissipative, but and in fact it's diffusive, but the parameter m is very large for that particular example. And so this is not a perfect separation, so to speak, of transport and diffusion. But at the same time, we didn't really think about it that way. That wasn't really the goal of making this definition. But I think it would be accurate for you to sort of mentally, as a mental model, to say, look, this m parameter is the way that we're separating things in a quantitative way, but strictly speaking, in the analysis, we don't actually say, let's consider diffusion and then let's consider transport. That's not a consideration that's made.
Great, thank you.
So let's see if there are other questions. It looks to me that there are no questions, so I think that we can thank again the speaker of today. So thank you, Akil, for this beautiful talk, really clear. Thank you. And I think that we can see each other next Tuesday for the next seminar. So thank you, everyone. And thank you again, Akil. Bye.
Thanks. Bye, everybody. Thank you.
Thanks, Akil.